Okay, good morning everyone. I hope we can start. So you can just type to say yes, we can start so that we proceed with where we ended last time. So if you're able to hear me, you can just tell me so that I can start with the lecture. Those who are able to hear me, if you're able to hear me, please, we can start with the lecture. You can just type, say you're able to hear me so that I can start lecturing. Okay, that's wonderful. Now, last time we looked at different types of differentiation. We looked at the different functions that we differentiated. There are those who are going to join us later, so we can't start waiting for people. So that's why I've just said no, we need to start. Then they'll be joining in the middle of the session. So what we are going to look at last time, after looking at the chain rule for differentiation, so today we are going to look at this type of differentiation which we call implicit differentiation. Now, as also like the way we were doing it last time, this is how also I'll be doing it this week, which means I'll be switching from the PowerPoint to the board and board to PowerPoint, just like that, just like they were doing it last time. So before, as I'm starting, so we are looking at what we call differentiation. So I would like to switch to the boards because this is what I'll be frequently using. So I guess everyone is able to see what is displayed on the board. No one is left behind. So okay, let me just push this camera. So we are looking at, our topic is differentiation, or let me just say implicit differentiation. Differentiation. I hope you're able to see what I'm writing on the board. I guess everyone is able to see what I'm writing on the board. So we are looking at what we mean by implicit differentiation is we are looking at the derivatives of implicit functions. Now, what is really an implicit function? So from the time we started differentiation, we have been looking at explicit functions. What I mean is explicit functions. Now the question is, what is an there is a difference. There is this explicit, there is an explicit function, and there is what we call implicit function. So whatever differentiation that we started with, we are doing explicit differentiation. Now, an example of if you are able to write, so an explicit function is any given function that you're able to write in the form y equal to f of x. So this kind of a function, we call it an explicit function. Now, examples of such function are, e.g., an example of such a function, we have y equal to, for example, x power 4 plus 2x squared minus 3. So this is an example of an explicit function. Other functions, we have y, which is equal to x, let me say 2x times the ln of x. This one is also an explicit function. So in general, if you have a function, which is this function has been written in terms of x and y, and you are able to write to make y the subject of that formula, if you're able to solve for y in that given function, then we call it an explicit function. Now, there are also other functions which are so difficult to solve for x and y. So you have other functions. These are functions like the implicit function. These are the types of functions that you cannot manage to make y the subject of the formula. An example is we have y power 3 plus 2x squared y minus, we have maybe 3x is equal to 4x cubed, maybe minus 4. So this type of a function, if I ask you to solve for y in this equation, it will be so difficult for you. Other examples, maybe we have x y power 2 minus 3x y is equal to 4y maybe minus 5. This type of a function is also, all these are some of the examples of implicit function. Now, the issue here is, what we are looking at is, how can we differentiate such type of functions? How can we find the derivative of such functions? Since you're able, because for you to differentiate, you are differentiating a function of y with a function of x. So you have y, you are differentiating y with respect to x. So this y is a function of a variable x. So in this scenario, you should be able to make y the subject of the formula, and then now you differentiate the function y with respect to x. Now, if you have a scenario like n of these two, if you have any of these two functions, now they are asking you to find the derivative of this function with respect to x. Now, how are you going to handle it? As such, you don't really need to worry. To differentiate such type of functions is now you use the method of implicit function. Now, the method of you use implicit differentiation. Now, when you are using the implicit differentiation, it also makes use of the chain rule. I remember the last lesson that we had last week was about the chain rule, on how you can differentiate using the chain rule. Now, under the chain rule, it uses this formula. Like I mentioned last time, I will not be really going into details of how they generated it. So it makes use of the formula under the chain rule. So what you need to do is, if you have such a function like this one, or let me give you a simpler one. For example, we have y squared minus 3x maybe is equal to 4y plus maybe 5xy. So if you have such kind of a formula, what you need to do is you differentiate both sides of the equation. So you're going to differentiate this side, you take the derivative with respect to x. Also, on the other side, you take the derivative with respect to x. So you take the derivatives, both sides, with respect to x. Now, how can you do that? Using the chain rule. Now, you're going to use the chain rule both sides. So you are differentiating this side with respect to x, you're also differentiating on the other side with respect to x. Now you make use of the chain rule. How does this chain rule being stated? The chain rule, it is stated as the derivative of u with respect to x, which will give you the derivative of u with respect to y multiplied by the derivative of y with respect to x. With respect to u. So this was supposed to be with respect to x. Now, after you do this, after you have differentiated with u with respect to x, which is got the derivative of u with respect to y, and then the derivative of y with respect to x, then what you're supposed to do now, after doing all this in this equation, you solve for the derivative of y with respect to x. So this is what you're going to do. You do this both sides, and then you make use of the chain rule in the process of making use of the chain rule, after you are done with your differentiation, then now you make the derivative of y with respect to u the subject, or you solve for it. Or in simpler form, when you are using function, for example, if you are using function, instead of you now handling it in this manner, if we use the function notation form, all you need to do is you are going to say the derivative with respect to x. Now, this is a function of y and x, where, so you have f of y, where y is also a function of x. So this is equal to, this is just, now when you apply this chain rule, which we have written here, this is just the same as the derivative with respect to y of f of y multiplied by the derivative of y with respect to x. So this is what you're going to do. So you either use, please remember you have these notes in your laptops. So all you need to do is just to open as I'm lecturing, then you are following. Okay, so you're going, this formula that I've written here is exactly the same as this formula. This one you're now writing it in function form. Okay, so if I write a function as, so if I write my function, so if I write my function as being y squared x minus maybe 3x squared is equal to 4y. So this is a function of x. This is a function of y. So it is f of y, maybe we can say is equal to 0. Now, where this y, remember that the same function you can also write it as y squared x minus 3x squared minus 4y is equal to 0. So what we are saying here is a function where x of y, which is equal to 0, where y is what? A function of the variable x. So to find the derivative of this type of a function, we use the chain rule with respect to the implicit function. So we use the implicit function way of differentiating. Now, so let's look at some examples concerning the implicit differentiation method. Let's look at some functions involving, so this is example number 22 from our notes. Example number 22, it says, I will not write the statement since you have the notes. Differentiate the following functions. So it's saying differentiate the following functions. Now, what are those functions? The first one is y to the power 3. The second one is 2y power 4. Then the third one, we are differentiating these functions with respect to x. Let me do this. We are differentiating these functions with respect to x. So the first one is y power 3. The second one is 2y power 4. And the third one is the sine of 3t. Okay, so let's look at the solution. Please, I hope everyone is able to see what is being displayed on the board. You can just type down there, tell me to say you are able to see. If you are unable to see, so that I know. Okay, so please, if you are able to see, I need to know. Okay, so let's look at the solution. So let's look at the solution to this example, to these three examples. So so let's look at the examples. Okay, according to the solution, the first thing that we need to do is, in one, we say let f of y be equal to y power 3. That's the first step we're supposed to take. So let f of y be equal to y power 3. I think my network has been cut off. Okay, my internet is very weak. Okay, so let's look at this example. Now, we are going to employ the use of this formula, which is here. So to do so, in doing so, now let's use this formula. So we are saying, if we let f of y, which is equal to y to the power 3, this means, now we want, remember that we are differentiating with respect to x. I know you are unable to see any variable x in this function. You are unable to see any variable x in this function, but the y you are seeing here is a function of our x. So to differentiate with respect to x, we are going to employ this formula, the derivative of f of y with respect to x, which is equal to the derivative of f of y with respect to y multiplied by the derivative of y with respect to x. Now, before we come to that, so what we have here, if we let f of y, which is equal to y to the power 3, then we are going to have the derivative of f of y with respect to y, which is just the same as the derivative with respect to y of y to the power 3. Now, using the derivative methods, this is just equal to 3y to the power 2. Okay. Then now, we now get this answer substitute it into the given formula. So then hence the derivative of f of y with respect to x, this is equal to the derivative of f of y with respect to y times the derivative of y with respect to x. Now the derivative of f of y with respect to x is 3y squared multiplied by the derivative of y with respect to x. So then what you have done, you have differentiated this function of y implicitly. So you don't need to go, you don't need to go any further, you just end there. Then number 2, so I'm going to run the top part. Part 2, I'll just go direct. Under part 2, so what we have is the derivative with respect to x. Our function in part 2 is 2y to the power 4. So the derivative of our function 2y power 4, this is equal to, the derivative with respect to y of this function 2y power 4 multiplied by the derivative of y with respect to x. And then, so this is going to give us, now this is going to give us 8y power 3 multiplied by the derivative of y with respect to x. So what you have done, you have differentiated the given function implicitly. So what you have done is you have differentiated the given function implicitly. However, there are other functions that you're going to be differentiating. We have also other examples, but I'll not look at those. So the last example, which is sine of 3t, I would love you to do it, because so you're going to differentiate this given function with respect to t. Or let me just do it, so for the sake of knowledge. Now let's look at this. Let's look at the third one. So the third one is the derivative with respect now to x of sine of t. This is equal to, now if you look at sine of t, this is sine of t, so it's a function of t, where t is a function of x. So this is the scenario here. So we have a function of t where t is a function of x. So this is the same as the derivative with respect to t of the sine of t times the derivative with respect to x of t. The derivative of t with respect to x, this will give us now the derivative of sine of t with respect to t. It's going to give us the cosine of t multiplied by the derivative of t with respect to x. Then that's the end of our first example where we're differentiating a given function in which we cannot make the variable differentiation as a subject of the formula, or the function of that you are supposed to differentiate with respect to x, the subject of that formula. However, so we also have example number 23 in your notes, which I would wish you to go and do at your own time. So however, so let's now look at other derivatives. Let's look at other differentiation concepts. Now, so when you look at the first part that we are, the first examples, we are just looking at these derivatives that do not involve either the product rule or the quotient rule. Now, in the next examples, so we are going to look at the derivatives of implicit functions which contains product or quotients. So we are going to now, in this next session of our lecture, we are now looking at derivatives of implicit functions that contains what? Which contains product or the quotient kind of functions. So you have these two functions which has been multiplied, but these two functions, you can't make y or the function itself, f of y, the subject of the formula. Now, we are going to look at the first example. In the first example, please, this is example number 20. Remember, I told you that example number 23 has been left as an exercise. Please handle it. So we are going to look at example number 24. This example, we are looking at this is under, so we are looking at derivatives. So we are looking at derivatives of implicit functions. Implicit functions containing products and quotients. So we are looking at derivatives of implicit functions containing products or quotients. Now, so let's look at example, one of the examples that involves such kind of function, which is example number 4. This example is saying differentiate, or rather determine, so we are saying differentiate the function, to x power 3 multiplied by y power 2 with respect to x. So we are going to differentiate this given function with respect to x. Now, instead of us making y the subject of the formula, we don't really need to do that. All we need to do is to use the implicit methods for differentiation. So you need to use the implicit differentiation method. So you need to use the method of differentiating implicitly to arrive at your answer, to arrive at the derivative of that given function. Now, the question that we need to ask ourselves is that how can we differentiate that given function? So if we look at the product rule, so in the product rule, for differentiation, so let your g of x be equal to, let our g of x be equal to 2x power 3. Okay, so we have g of x which is equal to 2x power 3, and our h of x be equal to y squared. That is, if we follow the product rule, this was supposed to be h of y. If you look at the way the product rule is defined, then according to the product rule states that whenever you have such a scenario, then the derivative with respect to x, okay, of the function. Now our function is 2x power 3 multiplied by y power 2. So according to the product rule, this is equal to the second function, which is y power 2 multiplied by the derivative with respect to x of the first function. Our first function is 2x power 3, then plus okay, let me put it here, plus the second function, or the first function, which is 2x power 3 multiplied by the derivative with respect to x of the second function, which is y squared. So this is what was supposed to happen. Now, the issue here is, after you have done that, this is equal to, now if you look at this part, you can only differentiate the square of y with respect to x implicitly. So you're going to differentiate the square of y with respect to x implicitly. Now, by implicit differentiation, so what we are going to have is, this is just y squared times the derivative with respect to x of 2x power 3, then plus 2 x power 3 multiplied by, so this I'll just put it in brackets like that. So the derivative of y power 2 with respect to x, it's going to give us the derivative with respect to y of y squared multiplied by the derivative with respect to x of the function y, because y is a function of x. So it will be the derivative of y squared with respect to y times the derivative of y with respect to x. Now, having done that, then you have this, you have y power 2, the derivative with respect to x of 2x power 3, it will just give us, we are going to get 6x squared, then plus 2x. Now, the derivative with respect to y of y power 2 is going to give us 2y, then multiplied by dy dx. After doing that, then when we simplify, what you're going to get is 6x squared y squared plus plus 4xy multiplied by dy dx. So what we have done, we have differentiated the given function, which is 2x power 3, which is 2 times x power 3 times y power 2. So you are done with that equation. Now, so let's look at also other examples that involves also differentiation. Now, the first one was talking about the derivatives of implicit functions containing the products of two functions. So we are differentiating of implicitly. So we are finding the derivatives of a given function implicitly. Now this function contains the product of two functions. We are applying the chain rule, by the way. So we are first applying the product rule. After applying the product rule, but because y is a function of x, then we apply the chain rule. So you are applying the process twice. So if you first apply the product rule, then after applying the product rule, then you apply the chain rule. Now after applying the chain rule, then you arrive at your final answer. Now let's look at example number 25. Now this example number 25, it involves the quotient rule with, at the same time, with respect to the implicit differentiation. So you are using the quotient rule, and also the implicit differentiation rule. Now, what does this example say? This example, which is example number 25 from your notes, it says that find the derivatives or differentiate the function 3y over 2x with respect to x. So similarly, in the quotient rule, if you look at in the quotient rule, so if we use the quotient rule, in the quotient rule, so we let our g of x be equal to 2x and our h of x be equal to 3y. So our g of x being equal to 2x and our h of x being equal to, or you can use f, being equal to 3y. Then, by the quotient rule of differentiation, applying the quotient rule first, before you apply the implicit differentiation rule, you first need to apply the quotient rule. So by the quotient rule of differentiation, we have the derivative with respect to x. Our function is 3y divided by 2x. Okay. Using the quotient rule, this is equal to the denominator multiplied by the derivative of the numerator minus the numerator, which is 3y, multiplied by the derivative of the denominator, which is 2x, everything over the square of the denominator. So now, this is equal to 2x. Now, if you look at the derivative with respect to x of 3y, you can only handle that using implicit differentiation. Here, this is the derivative of 2x with respect to x, so this is a function of x, so we don't need to apply implicit differentiation here, but here, this is 3y is a function of y, we are differentiating it with respect to x, so we need to apply implicit differentiation. So then, that means, applying the implicit differentiation, what you're going to get is the derivative, so we have something like 3, the derivative of y with respect to y times the derivative of y with respect to x, okay, minus 3y the derivative with respect to x of 2x, everything divided by 2x squared. After having done that, so the derivative of y with respect to y, since we are differentiating with respect to y, this will give us 1. So we have 2x, the derivative of y with respect to x is just the derivative of y with respect to x. So from here we are going to get a 3 times the derivative times the derivative of y with respect to x minus, this will be 3y. Inside we are going to have 2 because the derivative of 2x is just 2 over 2 squared is 4x squared. So then this is going to give us from which we are going to get 6x derivative with respect to x minus 6y everything over 4x squared. So that is what we are going to get. So the issue here is we need to find, now in this scenario what you need to do is we make the dy dx the subject of the formula if you want from here, because we have dy dx here, we also have d with respect of this function with respect to x. So you can either simplify it and come up with something very unique, but it's just one and the same thing. So all you need is just to leave it like this and then you are done with your differentiation. Okay, there is also another example that involves differentiation, which is example number, we have example number 26. So I'll be able to solve this one. I think this one will be the last example of this session. The rest you are going to be doing them at your own time, because we have other examples that involves also differentiation implicitly, the implicit differentiation in short. So some of the examples you'll be just doing them at your own time because they are already in your notes. The only thing that you need to do is to work on them. That's it. All right, so let's look at example number 26. I tried to make sure that you have a lot of examples within these questions. So let's look at example number 26. So let's look at example number 26. So example number 26. So I'm going to rub this part. So example number 26 says differentiate. This is our example 26. It says differentiate. So we differentiate z, which is a function of x squared plus 3x times the cosine of y. Now they are asking you to differentiate with respect to y. So these are some of the questions that you're going to be finding in an exam. Or test, you just see that they ask you to differentiate with respect to x or y. So one thing that you should remember is don't just look at the question, you just read differentiate, then you just look at the question and start differentiating. Now the question is, what are you differentiating with respect to? Are you differentiating with respect to x or are you differentiating with respect to y? So you have to be careful. You have to read the entire question up to the end. Then you find out what is the variable of differentiation. Am I differentiating with respect to x or am I differentiating with respect to y? Not to just read, no, since I'm differentiating, it's automatically I'm differentiating with respect to x because you have seen an x being as a variable being written within the given function. So that's not the scenario here. So in this case, we are differentiating with respect to y. So this means, but if you look at the function z, the function z is a function of x and y. Now, if we are differentiating with respect to y, this implies that this x will be a function of y. So the x is going to be a function of y. So let's look at the solution. You have the solution here. That's why my examples, I'm writing them according to the way they are in your lecture notes that I sent to you. So now let's look at this. Now, so in this case, we are going to apply the sum rule first, then you apply the product rule, then we apply the chain rule, then we apply the implicit rules of, so all these four you're going to apply. So what I'm trying to say, so if by the sum rule, product rule, we also have chain rule and implicit differentiation. Differentiation rule. So we are all these three because you see there is x squared plus 3x cos y. So here, sorry, this is 3y. Sorry, so this is 3y. So here we are first applying the sum rule of differentiation. Next, we are going to apply under this stage, under here, there will be an application of the product rule because you have a product of two functions, 3x and cos 3y. So these are different two functions will apply together. Now, if you look at cos 3y is a composite function. Cos 3y is a composite function, it's a compound function. Now, because it's a compound function, for us to differentiate it, we need to apply the chain rule. Now, because this x here and this x here are functions of y, because we are differentiating this given function z with respect to y, because this x, the square of x and x are functions of y, we are going to differentiate them implicitly. So you've seen, so all the four are in one given equation. So now, let's handle this one. So we are saying the derivative of this function z, now we are differentiating this function z with respect to y. This is equal to, which is just, we are differentiating this function. Our function z is x power 3 plus 3x times the cosine of 3y. So this will give us, using the sum rule, this is the derivative with respect to, y of x power 3 plus the derivative with respect to y of 3x times the cosine of 3y. Now, this is going to give us, let me just rewrite first this part by the product rule, then I'll come back and start going slowly by slowly. X cubed. So I've used the sum rule here. Now we are now applying the product rule there. So this is this will give us 3. Okay, so like I would just have to say this is the cosine of 3y times the derivative of 3x. Okay, then plus 3x. All right. Okay, times the derivative of the cosine of 3y, isn't it? So if you look at this function now, maybe I would want to apply the chain rule under here, because you have to apply the chain rule under this given this derivative with respect to y, So so this is the derivative the derivative of x cubed with respect to y. So if we apply the implicit differentiation method, so we are going to have the derivative of x power 3 with respect to x times, isn't it? Times the derivative of x with respect to y. Okay. Then plus the cosine of 3y multiplied by, again, we apply the chain rule here. We have 3, the derivative with respect to x of x multiplied by the derivative with respect of x with respect to y. That, because x is a function of y, then plus, now we have 3x. Now under here, we are differentiating with respect to y. This is cos 3y. Now we are going to apply the chain rule. Under the chain rule, so the derivative of cos 3y with respect to y, this is just the same as the derivative of y of 3y. Okay. Derivative with respect, the derivative of 3y with respect to y times the derivative of the cos, maybe we can call it the cos of theta with respect to how can we put this one? So it's oh, it was supposed to be the other way around, but either way I needed to write it in, but it will just confuse you. Let's just write it, but I would wish you to go and handle this one, because we know the chain rule. So if we substitute this to be y, then we differentiate it with respect to u. Okay, now so this is going to give us the derivative of x cubed with respect to x is going to give us 3x squared, the derivative with respect to y of x, plus, now 3 times the derivative of x with respect to x, derivative of x with respect to x would be 1, 1 times 3 to be 3, so it will be, then 3 times dx dy, it will just be 3 dx dy, so we are going to have the cosine of 3y multiplied by 3 times the derivative with respect to of x with respect to y, then plus, so we have here 3x, then the derivative of cos 3y is just 3 negative sine of 3y, because cos 3y is negative sine of 3y, then the derivative of 3y is 3. Then having written that, so we are going to have then now from there, so we are going to get, when we simplify, so we are going to have this is equal to 3x power 3 squared dx dy, then plus 3 cos 3y dx dy, then plus what we have there is also to be minus 9x sine 3y, and then you are done with your derivatives. Okay, if there is any error that you are able to spot, you can let me know, but from what we've done, I think it's perfect. So this is the solution to your question. So you have differentiated implicitly with respect to y. Now there is another example, which is example number 27, in which they are asking you to differentiate with respect to x, but I will not do that. Instead, example number 27, maybe let's look at it, example number 27, because it's involving a certain step which I need to explain. So that is example number 27. Let's go to example number 27. So So let's go to example number 27. Example number 27. Okay. I think this would be the last example. Under this, then we go to differentiation of trigonometric logarithmic functions. So this will be the last example under implicit differentiation. The rest of the examples you can find them in different books. Some of the books I already sent them to you, so you can just go in those books, go through and see what you can connect. Also, you can also find some of the works in Bed, John Bed, 6th edition, either 4th edition, 6th edition, Higher Engineering Mathematics. You can also find a lot of examples about talking about implicit differentiation. Now, let's look at the last example of under implicit differentiation. So this example says differentiate with respect to x, that is the given function 2y, the given function 2y squared. So we are differentiating 2y squared minus 5x power 4 minus 2 minus 7y cubed is equal to 0. So they are asking you to differentiate that given function with respect to x. So differentiate this given function with respect to x. So how are we supposed to handle this? It's in the same manner. So what we need to do in this scenario is each term is differentiated with respect to x. So you differentiate each term in this function with respect to x. This is an equation. You remember when we started about implicit differentiation, I mentioned to say you are going to differentiate both sides of the equation with respect to x. You will differentiate both sides of the equation with respect to x. Not where I just differentiate one side. No. If you have an equation like this one, then you're going to differentiate each side of this equation, both sides of this equation, with respect to x. So by doing so, in short, you are going to differentiate term by term. Each term must be differentiated with respect to x in this scenario. So we are going to have the derivative with respect to x of 2y power 2, okay, then minus the derivative with respect to x of 5x power 4, then minus the derivative with respect to x of 2, then minus the derivative with respect to x of 7x cubed, which is equal to the derivative with respect to x of the function 0. Okay. After doing that, so if you look at this derivative, this implies that now the derivative of y to the power 2 with respect to x, we are going to handle this using implicit differentiation. I don't know if I should start again going slowly by slowly explaining each and every part. I don't think so, but either way. So applying implicit differentiation here, so we have 2, we can just push it outside, then we are going to get the derivative with respect to y of y squared multiplied by the derivative with respect to x of y. Okay, but okay, I think this was supposed to be y, but then the derivative of 5x power 4 with respect to x, this will just give us minus 20x power 3. The derivative of a constant function is equal to 0 minus this. Also, we are going to have 7 multiplied by the derivative with respect to y of y power 3 multiplied by the derivative with respect to x of y, then is equal to the derivative of 0 is 0 because it's a constant function. Then from there, now we are going to get this will mean, let me just use the other part of the board. Okay, so this will mean the derivative of y power 2 with respect to y, it will give us 2y. Now 2y times 2 to give us 4y dy dx minus 20x, then minus that is 20x power 3, which is 3 there, 0, okay, minus, then the derivative of y power 3 with respect to y is 3y, so 3y squared, so 3y squared times 7 to give us negative 21y squared, so is equal to 0. Multiplied by dy dx, which will give us equal to 0. So this will imply, now, so if we rearrange, if we rearrange, rearranging, what I mean is, if we rearrange this, by rearranging I mean we want to make dy dx the subject. So if we rearrange this, what we are going to get is 4y dy dx minus 21y squared dy dx, so is equal to, this will be 20x power 3. After rearranging gives, this is what we're going to get. Then, now, in this scenario, you have dy dx, which is appearing in this function. So, now, if you look at this, rearranging will give this, which implies, but because dy dx and dy dx is common, we can have 4y minus 21y squared, open bracket, open circle bracket, close circle bracket, multiplied by dy dx, which is equal to 20x power 3. Then in this equation, this is an equation of y, x, and dy dx. So now, so say solving, if we solve for dy dx, we are going to obtain, so we are saying, if we make dy dx the subject of the formula, that means we are going to divide both sides of that equation by 4y minus 21y squared. So we divide, so in this equation, if we solve for dy dx, then we are going to get the derivative of y with respect to x to give us 20x power 3 divided by 4y, then minus 21y power 3. So what you have done now, you have completed your differentiation. So you are done with your differentiation of that function implicitly. So there are a lot of examples that involves differentiation implicitly, which, like example number 28, we have also 29 and 30, also 31, but these examples, I'll leave them to you to solve them, because they are already solved. All you need to do is just to go through and then you answer some questions that follow. You try to compare the answers that you have found with respect to what has been solved. Okay, so let's now look at the derivatives of logarithmic and exponential functions. So we are now going to look at the derivatives of logarithmic and exponential functions. So I'm going to wrap this part. I need to write the heading. So we are going to look at differentiation of logarithmic and exponential functions. So the derivative of logarithmic and exponential function make use of the chain rule and the derivatives of implicit function, or rather implicit differentiation. So it makes use of the chain rule, which is the differentiation of functions of a function or composition of functions, and it also makes use of the chain rule, implicit differentiation. So you use these two when you are differentiating the logarithmic and also exponential functions, which are also in the family of logarithms. Now, so our next part is differentiation of log and of logarithmic and exponential functions. So the derivatives, so we're now looking at the differentiation of logarithmic and exponential functions in that okay, so under this session, now so I need first, maybe before I go further, maybe you can ask questions. You can ask questions before I go further. Those with questions, please, you can ask questions before I start the new part of this session, which is differentiation of logarithmic and the exponential functions. Please, you can ask me questions. Please, can you ask questions? It's not too much. I'm waiting for questions, please. Yes, that is Mwangala Foloshi. Yeah, your question is correct. Yeah, your question is correct. So if they say with respect to y, so all the d's in the denominator must have to be dy up to the end, because you're differentiating with respect to y. If they say with respect to d, it will be d, or with respect to e, it will be d1, de. That's how it was supposed to appear in short. Okay, next question, please. Please, let's ask questions. This is the opportunity that we have. Okay, Kayanda Katongo. I think he just put x to the power 3 there, because when I was writing, I solved with respect to x power 3. I know in the example,
there is x squared, but when solving, I ended up using x power 3, but the concepts are the same. The concepts are the same, so you don't have to worry to say why did you use this. So you can also handle it when it's x to the power 2. Just try to do that, then you see what is going to happen. Okay, our next question. Next question, please. Let's have questions, please. Let questions flow. Before I continue to the next part. Because after this, then tomorrow, remember tomorrow we have to look at tomorrow as well as 8 hours, depending on internet. 8 hours, we are, no, maybe it's because I reach 8 hours. So I'm planning if we can start the class tomorrow as well as 8:30. Tomorrow we are starting integration. So those who like missing, please tell them to be always there. Okay, that is Nancy Kamwimba. In most cases, if I just say differentiate the given function, basically, if you are taking the derivatives, now you realize that you are able to make dy dx the subject of the formula in that derivative. Then if you just make it the subject in that scenario, just solve for dy dx. But there are other questions whereby there are other functions whereby you can't really make dy dx the subject in that scenario. So just leave it the way it is. But if moreover, in such questions, let me just put it in simpler terms. If you have such a question, I will ask you to say, find the derivative of this function and in its simplest form. So that means I've added the statement. In its simplest form means I want you to reduce it in such a way that you are able to make the dy dx the subject of the formula. I hope I've answered your question. So this one is, when do we have a make dy dx the subject of the formula? That's the same question I was explaining to Messi. When you are given a question, I think you're able to tell to say, in this question, I should be able to make dy dx the subject. Okay. In the process of solving, you're going to realize that the dy dx will be able to come out. It will be able to come out from there. Okay, this is Tolani. He's asking to say, when can you know on where to differentiate implicitly? Basically, let me give an example on the board before I come to differentiation of exponential functions. Before I come maybe to this one, maybe let me give just a simpler example. Okay, I give you a question like this. Sorry, let me just tune to my OBS. Okay, let me give you a scenario. Let me give you this scenario. For example, if you are given to say, let me just put a line here before I start with that. Okay, now if I give you this question to say, differentiate, so we have y power 4, let me even just start with x power 4 minus maybe y power 3. Now, in this scenario, I'm asking, there are two questions here. No, let me put it as part of the question. Maybe I give it, say, e.g., differentiate the function, maybe x power 4 minus 3y power 5. One, I say with respect of, let me just say with
respect to 1, let me say x, 2 with respect to y. Let's look at this scenario. I'm answering who's this person's question. I want you to determine how you can do that. That is in the way. I hope you are able to see what I'm writing on the board and you are able to follow. Please make sure that you follow. And everyone, please, can you make sure that we follow? There is also no, that's not. That is the Siamalua. You do not lose marks by doing the short way to arrive at your answer. Why I'm doing it in that manner, where I'm taking each and every step, splitting it and doing that, so that you can understand. But once you understand the concept, you don't really need to start going into details, and you already know those concepts, so you just need to go in a short format way, provided your answer, the final answer is correct. So I'm now answering. Okay. Since they already responded. Okay. Now let's look at this. Now the question here is, how can I know that under this part I should differentiate implicitly, and also under this part I shouldn't differentiate implicitly? So these are the scenarios that you're supposed to understand. So we differentiate. The function here is what? We have dx with respect to x to the power 3 minus 3y to the power 5 with respect to, the first part is with respect to x, the second part we are going to differentiate with respect to y. Now, we start with 1. 1, we are differentiating with respect to x. So we are going to have the derivative with respect to x. Our function is x cube, x to the power 4 minus 3y power 5. Using the difference rule, this is just the derivative with respect to x of x power 4 minus, which you can just write 3, the derivative with respect to y with respect to x of y power 5. Now look here. Now you are like the question that you asked. You are saying, now when can I tell which part should I differentiate implicitly? Now look at this. We are differentiating with respect to what? Are we differentiating with respect to y or with respect to x? So this means this part of the function, you just differentiate it explicitly, because this x power 4 is the function of x that you're differentiating with respect to x. But y to the power 5, this is a y which is the function of x that we're differentiating with respect to x. So this part, we differentiate it implicitly. Okay, now, so we are going to have, then now, this will give us 4x power 3 minus 3. So this part now, we are going to say the derivative of y with respect to 5, the derivative of y to the power 5 with respect to y, multiplied by dy, the derivative of y with respect to x, which will give us 4x power 3 minus 15y power 4 multiplied by dy dx. Now, if you have such a scenario, here you can't make dy dx the subject of the formula. Moreover, we have dy dx of this function. So even if you make it the subject of the formula, you're just complicating your life. So all you need to do is just to leave it like that. Now, that is 1. 1, we are differentiating with respect to what? With respect to x. In part 2, you see what was going to happen. We are differentiating with respect to y. So how do we handle? The starting is the same. So we are going to have, now here, we are going to differentiate with respect to y. Of which function? The function is x power 4 minus 3y power 5, which is just equal to, using the difference rule, the derivative with respect to y of x power 4 minus the derivative with respect to y of 3y
power 5. Now, here, which part are we supposed to do the implicit differentiation? Look, the variable of differentiation is y. Now, if you look at this part, we are differentiating x power 4 with respect to y. In this scenario now, it's the x which is the function of y. This one is the derivative of y with respect to y. So here, we can just differentiate explicitly here under this term, but in this term, we are going to differentiate implicitly. Okay, so this now is going to give us that part now, which is going to give us that now will be equal to the derivative with respect to x power 4 with respect to x multiplied by the derivative of x with respect to y. Then that other part by 3, the derivative of y power 5 with respect to y. Then this is going to give us, this will give us 3x power 3, the derivative of x with respect to y, minus, this will give us 15y power 4, because the derivative of y power 5 with respect to y to give us 5y power 4, 5 times 3 to give us 15. I hope Mbewe have answered your question. So this is how you need to recognize which part should I differentiate with respect to with using the implicit method, and which part should I use the explicit method. Okay, my internet though it's high, it's down, it's high, so please, you'll be experiencing some video hiccups, but either way you can just find time to go through again. You just go through the videos and you'll be solving the questions. Okay, now having answered your question, unless if you have more questions. No, Matthews, I'm not saying all implicit differentiation, depending on how the question has been phrased. Now, if you look at that, if it's in equation form, if the question they're asking you, if the function they're asking you to differentiate is in equation form, yes, then you can make dy dx the subject of the formula. Now, if you look at the example that I was given to explain Bewe's question, if you look at the way we have written it, we have not only made dy dx or the derivative of that function with respect to x, or the derivative of that function with respect to y, the subject of the formula. No, we have not done like dy dx the subject of the formula, or in the other one, we have not done dx dy the subject of the formula. All we did is just to solve it like in the simplest, to bring it to its simplest form, then you leave it there. Just leave it the way it is. So it depends on how the question, if the question has been given in equation form, yes, you have to make dy dx the subject of the formula. An example is, okay, I'll wrap this part. An example of your question, with respect to your question, for example, the same one that I'm just from giving you. For example, if I gave you like x power 4 minus 3y power 5, maybe it's equal to, maybe I can put any, provided there's an equal sign here, maybe it's equal to 0, or I can put even is equal to 3y. So basically, if you have such kind of equation, I can even put 3xy or xy. So if you have such type of equation, Mr. This one, Simbe. So if you have Simbe, so if you have such kind of equation, which is in equation form, and then they're asking you to find its derivative with respect to x or with respect to, then at the end of it all, you're supposed to make dy dx the subject of the formula. That is when you are asked to differentiate this given function with respect to x. But if again they ask you to find the derivative of this function with respect to y, then what you need to do is to make the dx dy the subject of the formula, provided and it's in equation form. But if it's not in equation form, then you can't manage to make dy dx. You can make dy dx the subject of the formula. But at the end of it, or if you realize, it's going to make it will be the derivative of that given function with divided by some other function that you have found, which is just the same thing. Then there's which is just the same thing if you just leave it the way it is in the first place, like the way we have done here. We have discovered that the derivative of this function with respect to y is equal to 3x squared dx dy minus 15y squared. Yes, you can make dx dy the subject of the formula here. That means it will be dx dy will be equal to the derivative of this function with respect to y plus 15y to the power 4 divided by 3x cubed. So which is just one and the same thing. Okay, I hope I've answered your question. Someone is asking me to say 4x power 3. Which part is that one now? I've been forgotten. Oh, yeah. Thank you for that. Yes, it was supposed to be 4. Please take note of this. It was supposed to be 4 here. 4x power 3, not the one I've written. Not the one I wrote at first. So please make sure that you change it to 4x. Okay, maybe I can continue from here now. Okay, I hope I've clarified your concept. So now, one thing that you should remember is that not every function is very simpler to differentiate. Why I'm saying so, there are always other functions that are so challenging to differentiate, even or very tedious to differentiate. So there are certain functions that contain more complicated products and quotient. So you have this function that is containing the quotient, which is more complicated to handle, or you have this function that is containing the product, which is more complicated to handle. So if you have such a scenario, so if you have such type of functions, then now you are going to bring, because they are very complicated to solve directly or using the implicit function, you might find when you try using the implicit function, it becomes even more complicated than you continue going implicitly. At the end of the day, you might get even confused. So it becomes very tedious to handle. So what you can do now, you bring in the method of differentiation, the technique of logarithmic differentiation. So you now employ the technique of logarithmic differentiation, which we are now going to handle. Now, for this logarithmic differentiation, so the differentiation of logarithmic function and exponential function make use of the laws of logarithms. Remember the laws of logarithms. The laws of logarithms, the product, the quotient law, the power rule. We have the power rule, the product rule, and the quotient rule. So we have all those laws. So those laws that you learned last semester, you learned logarithmic functions last semester. So all those laws that you saw will be applied in this part of our session. We also need to use the differentiation coefficients of logarithmic functions and also the differentiation of implicit functions. So you employ first the laws of logarithms, so then you employ the differential coefficients of logarithmic functions, then you're also going to employ the differentiation of implicit functions. So you employ all these three at the same time in this function, which is so complicated for you to handle. Being complicated does not mean you can't manage to differentiate it, but it will take time for you to find the derivative of that function. Now, let's look at, we are going to go in step by step. Each part we are going to differentiate it in step by step. The first part is we are going to look at derivative of. The first part is ln of x. Okay. And so the first part, we are going to look at derivative of logarithmic functions. Sorry, maybe I'm moving too fast. Let me just do this. Let me go with it step by step. Under this session, the first part of this session is we're going to look at derivatives of logarithmic functions. So this is part A. Now, under part A1, we start with derivative of ln x. Under the second part of this, the second part under logarithm, we are going to look at the general derivative of, for example, ln if you have a function f of x. So basically, I would ask you to research more. So they used implicit differentiation to come up with the derivative of ln of x. There was also an application of implicit differentiation to come up with the derivative of ln of x, ln of f of x. However, for now, I'll just ask you to understand it from the layman's point of view by just inspection. Then, and also you need to remember it, just need to understand it. If I start going through each and every step how they came up with that derivative, just might take time. So in short, we just need to see how we can handle this situation. So now we are saying if your function y is equal to ln of x, then the derivative with respect to x of y, which is equal to the derivative with respect to x of ln of x, this is equal to 1 over x. Now, if you look at this scenario, if you look at this, the final answer in this expression, this function, this equation. So we are saying the derivative with respect to x of the function ln of x, this is equal to 1 divided by x. So this x is the one which is under the ln function. Now the one, if you look at the derivative of x, the derivative of x is equal to 1. So then, now from this scenario, we have the general form. This means if y is equal to ln of f of x, then the derivative with respect to x of y, which is equal to the derivative with respect to x of the ln of f of x, this is equal to the derivative with respect to x of the function which is inside the ln of f of x divided by the function itself, which is just f prime of x divided by f of x. So just remember this should just be by your fingertips every time you see a function of that nature. This is what really happens. Now, if you look at the function, if we have ln of x, then this is equal to x down. Then what is the derivative of x? It is just 1, following this general form. So this is the general form of the derivative of ln of x. I guess you are following, all of you. I hope everyone is following, because after this we are going to break, because it is 11, so I think we'll break at 12 hours. Then we call it the end of the session. I hope everyone is following. Please just type to say we are following, then we'll be able to see how many are following, and those who are still behind, please Okay.
So then now we are going to look at some examples that involves derivatives of logarithmic functions. So basically what was done here is there was some kind of implicit differentiation which was involved to come up with this kind of derivative and this formula. It's not that someone just popped up and then dreamed and said, okay, this is how it was supposed to look like, but there's an implicit differentiation that is involved within this function.
Okay, thank you. If you are following, now let's look at some examples. So I'll wrap the heading to make my board look bigger, of which you've already understood what we're looking at. So we're looking at derivatives of the logarithmic function, which is the natural logarithmic function. Now let's look at some examples that involves the derivative of logarithmic function. In our notes, this is example number 32. So I'll write it also as example number 32. So what this example is asking us to there are about 5 questions in that example. I think all of you have the notes. There are about 5 questions. So all I need is just to pick, I'll pick 2. Maybe if you can tell me, okay, I'll pick 3. If you can tell me which one I should do, and then which one I should leave, just say maybe 1, 2, 3, and 4, or whichever ones that we can pick from there. Then we can continue. Okay, maybe I'll just pick on behalf for you. I'll pick for you guys. So we are saying differentiate with respect to x, the given function. The first one is, so I will not follow what is written in the, I'll just go directly. So let's start with the first one. It's saying the ln of a, that is ax plus b. The second one is the ln of x squared minus 3x plus 1. The third one is the ln of the sine of 3x. The fourth one is that is x squared times the ln of x. The fifth one is these are just simple questions which you just need. So it does not matter how the question has been phrased, but remember that you learn the first basic rules, because these basic rules are applied in each and every questions that you encounter concerning differentiation. So you need to apply the chain rule, you apply the quotient rule, the product rule, the sum rule, whatever kind of rule that you learned in any given type of a question. When you just look at the question, you'll be able to tell, say, I need to apply all those basic rules that we learned about differentiation. Now let's look. I'll do 1, 2, 3. The other ones you're going to do them because number 4 is just the use of product rule. Number 5 is also making use of the quotient rule. So I'll do 1, 2, 3. Now let's look at the solution. So we say now in each case, so in each case we are going to make use of the formula of, we are going to make use of this formula, the derivative with respect to x of ln of f of x, which is equal to the derivative of f of x divided by f of x. Now 1. In 1, we are going to say, let f of x, let f of x be equal to, let f of x be equal to that is ln of x, ln of ax plus b. Then the derivative with respect to x of this function, which is ln of ax plus b. We are supposed to say let f of x be equal to our function, let f of x be equal to ax plus b, not what I wrote at first, not what I wrote at first. So let's in that scenario, I think if you check from your notes, there was also a typo there. So then the derivative of ln of ax plus b, this is just equal to the derivative with respect to x of ax plus b divided by ax plus b. Now, using the sum rule in the numerator, so the derivative of ax with respect to x to give us a, the derivative of b with respect to x, so we are differentiating b with respect to x, so b is a constant. In this scenario, we take b to be a constant, so it will be equal to 0, so over ax plus b, where, so the a and b in this scenario are constants. Please don't look at them to be like functions of x, they are just constants, they are numbers, any numbers that you can think of. In the next one, still number 2, so from this function which has been given as ln of our function is x squared minus 3x then plus 1, let our function f of x, let our f of x be equal to x squared minus 3x plus 1. Then what happens? Then the derivative with respect to x of the ln of x squared minus 3x plus 1, this is equal to the derivative with respect to x of x squared minus 3x plus 1, everything divided by the function itself, which is x squared minus 3x plus 1, which will give you, now using the difference and sum rule, the derivative of x squared with respect to x is 2x, the derivative of minus the derivative of 3x with respect to x to give us 3, the derivative of 1 is 0, so over x squared minus 3x plus 1. Now we can't simplify anything there, so we just leave it the way it is. Okay. The next question is ln of sine 3x. So we have in this question, we are going to use the chain rule and also the derivative of the linear function rule. Now, so that is that should be number 3 or number 4, part 4. For the function ln of the sine of 3x, let f of x be equal to the sine of 3x. Now, if you look at the sine of 3x, the sine of 3x is a composite function, a compound function. This means we are supposed to differentiate it using the chain rule. Then if we let our f of x to be that, then the derivative with respect to x of ln of the sine of 3x, this is equal to, according to the logarithmic differentiation rule, this is equal to the derivative with respect to x of sine 3x divided by the sine 3x. Now, the derivative with respect to x of sine 3x, we are supposed to differentiate it using the chain rule. Now, applying the chain rule here, so when we apply the chain rule, this will give us 3 times the cosine of 3x divided by the sine of 3x. So that is by applying the chain rule. Either you can end there, or you can go further. 3 cos 3x over sine 3x, sine 3x divided by cos 3x, this will give us 3, which this is equal to cot 3x, the reciprocal of the cosine, of the tangent function, which is because cot theta is equal to cos theta divided by the sine of theta. So cot 3 theta will be equal to the cosine of 3 theta divided by the sine of 3 theta. Okay, having solved those questions, so you can also find certain questions like example number 33 after 32. So you have this function where you apply the product rule, then you apply the
Okay, please let's look at like I was saying, we also have example number 33. In example number 33, there is an issue of using also the chain rule. So there are a lot of you apply first the chain rule. First, in the first place you apply the product rule. After the product rule, you apply the chain rule. The chain rule, you apply integration of logarithmic functions at the goal. So everything are happening at the same time. So make sure that you go through that question. If you have any challenges, then you can contact the tutors. You can contact me. We'll be able to handle it. So by tomorrow, please try to handle it. If you are failing to handle it, then by tomorrow we can solve it. That is example number 33. Find means and ways on how you can handle it yourself. Then you see what you can what you can grasp from there. If still it's giving you challenges, then just post in the group that it's giving you challenges. Then we can handle it tomorrow. Okay, now let's look at. We also have other examples like example number 34. Also example, just example number 34, which also involves the you first applying the logarithmic function. After applying the logarithmic properties, then you differentiate. It's also one of them. Instead of you using the quotient rule, if you look at this example number 34, the way it is, it's so tedious to handle if you apply the quotient rule and the product rule at the core. Because it will be so much it will be very much involving for you to handle it. But if you apply first the limit functions both sides, then you differentiate implicitly on the left hand side, and you differentiate using the logarithmic form of way of differentiating it on the right hand side. Your final answer will come out in a straightforward manner. Now, if like you force yourself to differentiate that kind of a function using the quotient and the product rule, it will be very challenging. Maybe with time, let me check my time. Okay, I still have some minutes to 12 hours, though that means we can finish at 12:30. I'll just extend it. Once we are done with this part, we're not going to have a class in the afternoon. We are just handling this same class. This will be like the last one. Then until tomorrow, when we look at, I think the derivative of inverse trigonometric function, we'll look at it tomorrow in the first 1 hour. Then in the last, that's what I'm saying, we start at 8:30. Then the other one, we are going to start integration. Then I think next week we are going only to look at applications. We are going to concentrate on applications of differentiation and integration. Then the other week, Friday, we are going to write your test. Maths test, it's if you see from the post, it's only written to be communicated to. So I'm communicating to you now that your test, you write it in the last week. Maybe I'll just put it on Thursday, so that in the same next week you have some tutorials with the tutors. During the physics, during the biology classes, that's when I'm going to meet you. And maths, on Monday we are going to do maths. But during the physics and chemistry, I'm told you are going to write your tests. So now, though there are some of you who are telling your colleagues that the exam will only contain 2 topics. Who told you that? The exam will contain everything that you've learned this week. I mean, everything that you've learned this semester. So test 2 is the one that will only comprise of integration and differentiation. That's all. Only 2 topics. So in short, test 2 will only comprise of calculus. That's all. So please don't confuse your colleagues by saying no, the exam will only contain 2 topics. Okay, now so let's look at a question. Example number 34. I think I need to answer to solve this question. So example 34. Now this example, the other examples we are going to handle them. That is example number 33, which I've left hanging because I know you'll be able to handle them. Now let's look at example number 34. It's saying
For example, maybe I don't even use to say use logarithmic differentiation to differentiate this function. For example, I give it say differentiate y, differentiate with respect to x, the function y, which is given by x plus 1, then x minus 2 power 3 over x minus 3. So they're asking you to differentiate this function with respect to x, and the function given is x, y, which is equal to x plus 1 multiplied by x, the x minus 2 to the power 3, everything divided by x minus 3. Now, I give you this kind of equation in an exam. So one thing that you should, how can you handle, if you use the quotient rule, you have to apply the product from the quotient rule at the same time. You apply all these in the same solving. Now, it will make your life so tedious in that when you reach at this stage, then you apply the chain rule or you expand it, because you expand x minus 2 to the power 3, or you apply the chain rule. So you're going to apply the chain rule under this stage. When you find the derivative of x minus 2 to the power 3, then because there's a product here, you're going to apply the product rule. Now, because there's a quotient, so you're going to apply both the chain rule, the product rule, and the quotient rule at a go. Now, to make it easy, then you use the logarithmic differentiation. So let's look at the solution. So in this case, we are going to use logarithmic differentiation. Now, how are we going to do that? By first taking natural logarithms, both sides of the equation. That is, now how can we do that? This is how we are going to do it. So if you take natural logarithms both sides of that equation, y equal to x plus 1 times x minus 2 squared divided by x minus 3. So you take natural logarithms both sides. So we are going to have ln of y is equal to ln of x plus 1 x minus 2 power 3, everything over x minus 3. Now, if you take the ln, now using the laws of logarithms, so if you use the laws of logarithms, so using the laws of logarithmic functions, this is the same as ln of, so we have x plus 1, x minus 2 cubed. So I'm using the quotient rule minus ln of x minus 3. So I'm using the quotient rule now. So I'm applying the quotient rule there. Now, if you look at this part, you apply the product rule of logarithmic functions. This is equal to ln of x plus 1 plus ln of x minus 2 power 3, then minus ln of x minus 3. Now, here you now apply the power rule. So this is just the same as ln of x plus 1 plus 3 times ln of x minus 2 minus ln of x minus 3. So this is the only stage that you need to handle, after which then you differentiate using logarithmic functions. Moreover, on the right hand side, you do it implicitly. Okay, now, so I'm writing this part. Then, the derivative with respect to x of ln of y, this is equal to the derivative with respect to x of ln of x plus 1 plus the derivative with respect to x. So ln of x plus 1 plus the derivative with respect to x of the function that is 3 times ln of x minus 2, okay, minus the derivative with respect to x of ln of x minus 3. Okay, there we go. All right. So now on the right hand side we differentiate implicitly on the right hand side, and this gives when we differentiate on the right hand side, maybe let me go step by step. On the right hand side, we are going to differentiate ln of y with respect to x. So this is an implicit function because y is a function of x. So we are going to have on the right hand side, what we are going to have is the derivative with respect to y of ln of y times the derivative with respect to x of y, which is equal to on the left hand side. On the right hand side, what we are going to have is the derivative with respect to x of x plus 1 over x plus 1 plus 3 times the derivative with respect to x of x minus 2 over x minus 2 according to the logarithmic differentiation rule, then minus the derivative with respect to x of x minus 3, everything over x minus 3. Now, the derivative with respect to the derivative of ln of y with respect to y is 1 over y dy dx is equal to the derivative of x plus 1 with respect to x. The derivative of x is with respect to x is 1. The derivative of 1 is 0. So we are going to have 1 over x plus 1 plus, on top we are going to have 3 over x minus 2 minus, we are going to have 1 over x minus 3. Okay, from this, now we want to make, so solving, because y is alone, so dy dx we can solve, because dy dx is solvable, is you can make, in short, we can make dy dx the subject of the formula. So solving for dy dx, we get what we are going to obtain after we make dy dx the subject of the formula. So we are going to have this final answer to this question, which is so we are going to get dy dx is equal to y times multiplied by 1 over x plus 1 minus plus 3 over x minus 2 minus 1 over x minus 3. But then the question is, what is y? What is y? This y is equal, so this is just equal to, your y was equal to x plus 1 multiplied by x minus 2 power 3 divided by x minus 3. So all the whole of this is in position of y divided by 1 over x plus 1 plus 3 over x minus 3, minus 2, then minus 1 over x minus 3. So that is your final answer to this question. Okay. Okay, having solved this question, then I would want us to go back to now to proceed, to go to the next part of differentiation, which is the derivative of exponential functions. We know what an exponential function is, so we have about 3 scenarios. So once we are done today, this is 11:57, so I say by 12:30 we'll be out of this place, because we started a bit late, somewhere around 10, so it's just we're still within the possible time, which is 2 hours. Yeah, because okay, now let's look at some last part of differentiation for today's session. So now we are looking at the derivative of exponential functions. Exponential functions this is B, part B. Now under part 1, we are first going to start by looking at the derivative of e to the power x. After that, okay, I think my marker is going faint. I'll try to use different markers for solving purpose. After that, then we are going to look at the derivative of functions of the form, that is number 2, derivative of functions of the form e to the power f of x. So we have 2 scenarios for derivatives. Okay, maybe I can continue. Let's check on these kind of functions that we are looking at. E to the power x, which is an exponential function. There is also another form, but that one I'll look at it later first. Let's first concentrate on the functions that I've given you above, which are involving there's also so let's look at first the first 2, of which I'm going to give you only 2 examples in this scenario, because the rest are just for follow-ups, so that we work on our questions. Hello? There's much.
Okay, so now let's look at this scenario. So derivative of, so we are saying if y is equal to f, or so if y is equal to e to the power x, then the derivative with respect to x of y, which is the derivative with respect to x of e to the power x, this is equal to e to the power x. This is the only function whose derivative is the function itself. So this is the only unique function. However, if y is equal to e to the power f of x, then the derivative of y with respect to x, which is just the derivative of e to the power f of x with respect to x, this is equal to just the same as the derivative with respect to x of the function itself multiplied by of f of x multiplied by the entire function itself. So which is just f prime of x times e to the power f of x. Please, there is always this confusion that arises to when it comes to differentiating, when you are between the logarithmic function and the exponential function differentiations. So you need to be able to differentiate when you are solving. When you look at the question, what should I handle? What type of function am I given? Is it an exponential function? Is it an algebraic function? Or is it a logarithmic function? So you need to have those scenarios. Now, so now, having said that, then we are going to look at some examples. We are going to look at some examples that involves this type of functions. So let's look at some examples that involve this type of functions. I'll look at the third one later. So I'll wrap even this other part for easy solving so that we can solve properly. So this is example 35. It says differentiate with respect to x. Differentiate with respect to x. The first one is e to the power 3x minus 2. The second one is e to the power sine of 2x. The third one, I'll just do 2, 3, e to the power, x, e to the power negative 2x. The last one, but not the least, however, I'll just do 2 from here, is e to the power ln of 2x divided by 2x plus 3. So I'm just going to do 1 and the 3. The other ones you're going to handle them at your own time. So do 1, and I'll also do part 3. Then part 2 and part 4, you can handle them. Find the spare time to handle these questions. Now, let's look at the solution. So in each case, we are going to make use of the formula, the derivative
with respect to x of e to the power f of x is equal to the derivative of f of x multiplied by e to the power f of x. Okay, let's start with 1. So for y being equal to, for e to the power 3x minus 2, so we let f of x be equal to 3x minus 2, then the derivative with respect to x of e to the power 3x minus 2, this is just equal to the derivative with respect to x. Our f of x is 3x minus 2 multiplied by e to the power 3x minus 2, which will give us 3 e to the power 3x minus 2. Then we are done. The third one, like I mentioned, I only do about 2 of these. The other ones, you are going to handle them. So for the second one, I've left it. It's an exercise. So the third one, for the function, which is x e to the power negative 2x, which is the third one, I should hope so. We let still, that's not a big deal, but we're supposed to use the product rule. So what we have still, we are just going to let f of x be equal to negative 2x and g of x be equal to x. Then by the product rule, then the derivative with respect to x of x e to the power negative 2x. First thing first, you apply the product rule. Now the product rule says the second function multiplied by the derivative of the first function plus the first function multiplied by the derivative of the second function. This is how the product rule says. Now, if you look at in the second term of this expression, we have the derivative of e to the power negative 2x, which is an exponential function. So we apply the differentiation of the exponential function. So we are going to have that expression x. So in this one, then we are going to have x multiplied by the derivative with respect to x of negative 2x multiplied by e to the power negative 2x. That is what we are going to get. Then when we simplify, the derivative of x with respect to x is 1 times e to the power negative 2x to be to be e to the power negative 2x plus the derivative of negative 2x is negative 2 times x. Then at the same time, negative 2 times x times e to the power, so we are going to have a minus 2x e to the power negative 2x. You can either leave it there. That is the final answer, or if you want, you can factor out the e to the power negative 2x, and then what you're going to get is what I'm writing down here. We have 1. This will give us, if you want, you can factorize 1 minus 2x, then e negative 2x. Then you are done. That is your final answer. You can either post-factorize it or pre-factorize it. It's just one and the same thing. Okay. we need to look at the last part. What I want tomorrow, not us to have a lot of work, because we are only going to have the time from 8 hours to 12 hours, somewhere there, then we are going to end the class. So we want, if we can finish this session tomorrow and we start integration where possible. So we are going to look at the last but not the least of this session, which is number 3 under logarithmic exponential differentiation. We are looking at derivatives of a function such as f of x, everything to the power x. So the derivative of such type of functions, such functions include functions of the form such functions include functions of the form. So the type of functions that can be written in that form, for example, if they ask you to find the derivative of x to the power x, or they ask you to find the derivative of x plus 2 the power x, or a function such as the xth root of x minus 1, it is also in this form, the function of x raised to the power another function of x, or you have x squared minus 3x plus 1, everything to the power 2x plus 5. It is also of this form. Now the question is, how can we differentiate such types of functions? So to differentiate, if you're given a function of this nature, so etc, if you're given a function of that nature, to find its derivative, you need to use the logarithmic differentiation. Otherwise, you will not manage to use any other form of differentiation to arrive at the solution to such given functions, to arrive at the derivative of such given functions. Okay, in so doing, we are going to look at only 2 examples. The rest, please find time to go through them. So I'll combine these examples in one. Like I'm saying, I'll combine them in one. So to be just like one question. So I'll make it to be like example number, which is example number 36. So I'll combine 36 and 37 as one example. So so we are saying this is example 36. So differentiate. So we are saying the question says differentiate with respect to x, each of the functions Now, what are these functions? The first one is y equal to x power x. The second one is y, number 2, it's y equal to the xth root of x plus 1. The third one, and the last is y equal to 3 to the power x squared plus 1. So I'll handle this question one by one. Once we do the last question, then that will be the end of this session today. Then when we meet tomorrow, we are going to look at the last two parts of differentiation. Then we are going to start integration. Integration, I'm also going to do just the basic properties of integration, and then the methods of integration, we are going to do them next week. Okay, so let's look at the solution now. Solution. Number 1. Y is equal to x power x. How can we differentiate this function? It's so impossible to differentiate such type of a function provided we don't apply natural logarithms both sides. If we don't apply differentiation by natural logarithms, then we can't manage to find the derivative of that function. Now, the Neperian logarithms is just the natural logarithm, which is one and the same thing. So, in the first part, so what you need to do here is take natural logarithms both sides of that equation. So what you're going to get is ln of y is equal to ln of x to the power x. Now ln of x power x, using the power rule for logarithms, for logarithmic functions, this is just x multiplied by ln of x. Now this one now becomes easy for us to differentiate. Hence the derivative with respect to x of ln of y is equal to the derivative with respect to x of our new function now, x times ln of x. On the left hand side of this equation, we apply the implicit differentiation. But on the left hand side of our equation, we apply the logarithmic differentiation with respect to the product rule at the same time. This side we apply logarithmic differentiation and also implicit differentiation on the left hand side. On the right hand side of this equation, we apply the product rule. After applying the product rule, then we apply also the normal differentiation and also the logarithmic differentiation. Now, on the right hand side, this is the same as derivative of ln of y with respect to x or with respect to y implicitly multiplied by the derivative of y with respect to x. That's what implicit differentiation states, which is equal to the x times the derivative with respect of ln of x with respect to x, then plus ln of x multiplied by the derivative of x with respect to x. Now, the derivative of ln of y with respect to y, this will give us 1 over y multiplied by dy dx, which is equal to x. The derivative of ln of x is 1 over x plus ln of x. The derivative of x with respect to x is 1. Okay, now, so then, after writing that, what we're supposed to do then is simplify that, solve and simplify. So this will then give us, when we simplify, we have 1 over y dy dx, which is equal to 1 plus ln of x. Now, when we reach this stage, so we say we now solving for dy dx. What do we get? Making dy dx the subject of the formula because it's straightforward. So we are going to have dy dx is equal to y multiplied by 1 plus ln of x. Now, but what is y? What was our y in the first place? Our y was equal to what? Our y was x to the power x, so multiplied by 1 plus ln of x. Then you are done with your solution. So you have found the derivative of x to the power x. However, the last also I'm going to mention to say part 2. In part 2 of our question, I'll leave it as an exercise. Basically, you already have the example in your books, in your lecture notes, so all you need is just to go through it and solve it and see what you're going to arrive at, and then make some comparisons with what we have. So let's go to part 3 of our example, which is the last part of this example, and we can call it the day for today. So the last example is, which is number 3. We are saying y is equal to 3 to the power x squared plus 1. So if we taking natural logarithms, both sides gives the ln of y, which is equal to 3x squared plus 1. Which is equal to also the ln of 3x squared plus 1. Then this is going to give us, using the power rule on the left hand side, on the right hand side, we are going to have x squared plus 1 times ln of 3. Now, we can split this, or if you don't want to split it, you can just use the product rule anyway, which is just going to work. So, thus, the derivative with respect to x of ln of y, this is just the same as the derivative with respect to x of x squared plus 1 times ln of 3. Remember, ln of 3 is just a number, so it's a constant. Ln, if you punch on your calculator ln of 3, it will give you a number. This is not a variable, so it's a constant. So now, if we apply the product rule for differentiation on the right hand side and also the implicit differentiation rule on the left hand side, so we have the derivative of ln of y with respect to y times the derivative of y with respect to x, which is equal to ln of 3 times the derivative with respect to x of x squared plus 1, then plus x squared plus 1 multiplied by the derivative with respect to x of ln of 3. Now, on the right hand side, left hand side, sorry, we are going to have this which gives 1 over y dy dx is equal to, now the derivative of x squared plus 1 with respect to x is just 2x. So 2x times ln of 3 to give us 2x ln of 3 plus, now the derivative of 3x is a constant, so this is going to give us 0. So 0 times x squared plus 1 to give us 0. So then, so that's the final answer. Now, then when we are here, so solving for dy dx, what are we going to get? We are going to get dy dx is equal to y times 2x ln of 3. Okay, but what is y? If you look at y, our y is equal to 3 times x squared plus 1 multiplied by 2x ln of 3. But if you look at 2x ln of 3, this is just, you can either leave it there or you can reduce it further. So there are two ways here. You can either leave it there as your final answer, or you can go further and bring it. You can go further and bring this to this form. So you have 3x squared plus 1. Now 2x times ln of 3. This is just ln of 3 to the power 2x. We can also go further, so this is just, or this is equal to that, or we can also go further. You can either end here, or you can go further and reduce it further. You continue going and going and going, and then others, they can write this is ln of 3 to the power 2x times 3 x squared plus 1. You can also write it like that, or you can write it like that, or you can just leave it there. So thank you for your time and for listening for this session. So this is the end of our session for today. We are going to meet tomorrow again. Like I mentioned, tomorrow we are going to start the class as early as 8:30. So enjoy your day, enjoy your lunch, go through whatever we've solved. So just go through, then from there, then we'll see how far we can go. Thank you very much for your time. So I'm logging out, unless if you have questions for me that you need to ask me within the 2 minutes, which are remaining. So I only have 5 minutes. So, it's already 12:30 like I mentioned, but I will give you 5 minutes if you have questions that you need clarity. Please, the floor is open. Those with questions, please, you can ask. Okay, no questions. Please enjoy your day. This is the end of the lecture. Please inform your colleagues, those who are fond of missing, and they're the ones who are bringing wrong information to others to say, no, the lecturer said there will only be this number of topics. Don't listen to people. The number of topics that you're going to do in the exam, we are going to post them in the last week of learning. How many topics that are going to come in the exam, not what your colleagues are telling you now. Please listen to what the lecturers say, not what someone told you we usually, whatever we say, we usually post it on Moodle. Every one of you has Moodle. All right, this is the end of the class.